All right, guys, we're going to go ahead and get started now. So just so everyone's clear, we're just going to do a brief intro. We have this, we're recording this, and we will be posting it again on YouTube. We created a YouTube channel for the class, so any pre-exam reviews, the post-exam reviews, everyone will be posted in the same place. As far as this exam, everyone should know it's the multiple choice exam, the mini test for chapter 14. So there will be no free response questions on it. One thing I would definitely do as you're studying for the exam is check out the review key online if you haven't already done it from the worksheet that we did in class today. Make sure that you know how to do all those problems. We feel like those were good review for what this test should be on. Since we're videoing it, we're going to try and get to all of your questions, but if there's too many, we're just going to have to ask you to hold on so we can continue with the review. But please come up to us afterwards. We're going to stick around for a few minutes, and we'd love to answer any more questions that you have after the review. One more thing about Braden and I, we're really here to help you. So, we do these reviews for you guys. We want you guys to succeed in this class and do well. So we're up to any feedback that you guys have for us. Please let us know. Again, we're here for you. If there's something that you're confused about before you know the next test is coming, just shoot us an email and say, hey, can you guys touch on this? Because we do our best to gather information that we think will be pertinent for the test. But if you guys are struggling with one particular thing, then we can know about that, and then we can address it in our review. So, getting started.
Okay, so like Corbin said, for a lot of these reviews, what we do is we try to think about what it was like when we took the test. Maybe it's a particular subject or something that seemed to fool us or trick us a little bit, and or the little mistakes that we made, especially on our free response exam. I know, just recapping, everybody did really good on that, and so we feel really good about your guys' performance across the board as a class. And I know, talking to several of the students in my recitations, usually it was just the really small things, maybe a unit or something like that was missed, but not like a big error in understanding of a large concept. So that was really good. And again, rewatch these videos or go over your material in the notes you're taking in class. And one of my suggestions that I give to some students is after you do these long problems, like right now we're doing ice tables. That's a pretty extensive problem. When you finish a problem like that, before you just move on to the next one, what I would do is I would look up for my test for 5 seconds, maybe look at the wall in the testing center, wherever you are, and think to yourself, what is a common mistake that I usually make on a problem like this, or that students make? Think about what it is, and then go back through what you did briefly. And sometimes you'll see, oh my gosh, I didn't convert to kilojoules, or I didn't use the right constant, or I didn't square my equilibrium expression for my product. These small things that we do wrong. So that's a suggestion that I'll give you guys. I think that a few of you will see as you go back through your free response exam we just took. Maybe that type of approach would have saved you just a few more points. And that should make a difference in the end, okay? So to start off, I've written these graphs here, okay? These 3 graphs on the board. Now this is to get us thinking, get us started with understanding, what we've been talking about with our free response exam we just finished, and trying to mesh it with equilibrium. So let's look at these for just a minute. What I want you to do is understand that it's this simple equation, right? We have A goes to B. We have 3 graphs for this. My x-axis for each graph is time, okay? And each of these lines just corresponds to one of the species in this reaction. We have the concentration of A and the concentration of B for each line. Now what I want you guys to do is think about it for 15 seconds. What could the y-axis potentially be for each one of these? Now between only 2 options, between rate or concentration. Okay, rate and concentration. Okay, so that's what I want you guys to think about. What could this be, rate or concentration? Potentially both, right? So think about it for just a few seconds, and then we'll touch on that. This is what I would call a problem maybe you've only seen once or twice, but it could potentially be on your exam. It could fool you. Okay. Okay, so let's talk about it. I know I didn't give you very much time, but let's already go through it and try to figure out what could be the correct y-axis here. So what I'm trying to do is have you guys incorporate kinetics, which we just finished, with equilibrium and how they differ. In this first one right here, right, we are looking at this concentration of B that obviously starts low, and as the time progresses, we must be forming that as this concentration increases, or whatever we're measuring as B is increasing, and A starts high at 0 and is decreasing. And we notice that A is a reactant, B is a product, so this is making sense. What could potentially then be my y-axis here? Concentration, right? That makes sense. So let's talk about rate. Can it be rate? Why can it not be rate? Why can rate not work for this? Right. He said the rates would have to be equal, right? And that's exactly what I wanted to get at. This is something you all understand, but maybe on the test, if you were to see a problem like this, you go, wait, I don't know. This is throwing me off. To try to put those two concepts together, rate, when we were doing kinematics, when we were doing kinetics, the rate of the forward and reverse reaction have to equal one another. So there really is only one graph in this series that we can use rate as our y-axis, and that would be this one, where the rate of reaction A, or the forward reaction, is equal to the rate of reaction B, right? That's when we know that we're at equilibrium. But over here, this couldn't be rate, because if it was, I have a different type of rate for B forming and A forming, right? So they're really not in equilibrium, okay? Over here now, I could have concentration as my y-axis as well. I can. Because what we're trying to explain here as well is sometimes when we think of the word equilibrium, we think of something that has to be 5 equals 5 or 10 equals 10. The both sides of my products and reactants, they have to equal each other. And we know through experience, through the problems we're doing, that that is not true. Right? Equilibrium just means it's at the point when this is occurring, when the rates of those reactions, forward and reverse, are equal to one another. That could mean that I make a ton of products in this reaction, and at equilibrium, I mostly have products, right? But that means my rates are still the same. So if you get a question where you're asked to pick the right graph for a certain equation, you've kind of gotten a little pre-show to something like that, or had a little bit more experience with choosing the right graph. So not that difficult, but very important, okay? Any questions specifically on this? Yeah?
Could that double graph potentially be a graph of concentration as well?
It can potentially be a graph of concentration as well. So what she's saying is, yes, in some cases we do have a 5 equals 5 equilibrium where they really are right in the middle. And if you had that a case like that, what would you think your K value would be like? We can't put a definite number on it, but we can kind of guesstimate and say, well, if I have a 10 equals 10 situation where my concentrations are equal at equilibrium, I probably don't have a K value that's super small or really reactant favored, or super big and really product favored. So just to kind of tie those two things together as well. Okay? Yeah?
So what was the last graph?
Right here?
Yeah.
So this last graph can only be concentration. So the first can only be concentration. The middle can also be concentration, and this can only be concentration. The middle can be rate as well, but none of these two can be rate. Right? Only the middle one can have rate as its y-axis. Okay? Okay.
All right, so next we're going to talk about Le Chatelier's principle. This is something that you guys should be familiar with. Basically, the entire chapter comes down to these principles right here. So we're just going to go through them. There's 4 factors that will affect which way a reaction will go, whether it's going to drive to the left or whether it's going to drive to the right. So the first one of these is concentration. And the easiest way to think about it is, am I losing or gaining concentration of a specific reactant or a specific product? So if we look at this hypothetical equation, if I'm told that my concentration of my product is decreased, which way is my equilibrium going to shift? To the right, right, to make up for it. The equilibrium is always going to want to make up for the disturbance that you did to it. Okay? So, second one, volume and pressure. The main thing to know is I would just memorize this trend that if you lower the pressure in your system, what you're doing in these situations is you're increasing the volume. right? So if we have a closed container and we increase the volume of that container, our pressure is going to naturally decrease. And when our pressure decreases, it's going to cause a disturbance in our equilibrium. And what's going to happen is it's going to shift to the side with less moles. Yeah.
Wouldn't that happen when you increase the pressure?
Oh, I'm sorry, I wrote this wrong. I think I meant to draw this up arrow right here. Yeah, thanks for catching that. So if we decrease our pressure by increasing our volume, then it's going to shift to the side with, now I'm getting confused, with more moles. Okay? So less pressure, more moles. More pressure, less moles. Everyone clear on that? Any questions on that? Okay?
So is that basically saying that when you increase the pressure, it's making the side with less moles more reactive with each other?
Yeah, what it's saying is it's gonna, so if we have this equation right here, we have 2 moles on this side and 1 mole on this side, right? So if we increase or decrease our pressure, it's causing a disturbance in our equilibrium, and now our reaction is gonna drive either left or right to make up for that. So in this example, if we increase our pressure, it's gonna shift to the side with less moles, and vice versa is also true. Okay, so next one would be temperature. You guys had an example about this on your worksheet today in lecture. The easiest way to think about temperature is our temperature a reactant or a product? Okay? So for an endothermic reaction, is heat a reactant or a product? Reactant. And it's a product for exothermic. So let's say I draw this out right here, and I say this is an endothermic reaction. Exothermic reaction. So I have heat as a product. So if I increase the temperature of this system, which way is my equilibrium going to be shifted? To the left. And if I decrease the temperature, which way is going to be shifted? It works the same as concentrations. If you think about it as a product or a reactant, whichever one you increase or whichever one you decrease is going to determine the way that it shifts. Okay? And the last one is catalyst. What does a catalyst do to our equilibrium? So if we have a reaction that's already at equilibrium, what does adding a catalyst do? Nothing. Exactly. So catalysts, what they do is they lower the activation energy. They actually won't affect the equilibrium at all. What it can do is help your reaction get to equilibrium faster, but it won't actually affect the equilibrium. And if you're already at equilibrium, then you're there. Your rates are the same, like Braden was saying, and so adding a catalyst is not going to do anything. So for a little application of this, okay, we're going to do this. Yeah, go ahead.
So if I understand right, it would increase the rates but not change equilibrium, right?
Exactly. So if we're not at equilibrium, if we add a catalyst, it can help me get to equilibrium faster. But it's not going to change the equilibrium constant at all. Any other questions on those, Le Chatelier's? Yeah.
So is the equilibrium constant only temperature dependent?
Mm-hmm. Yep.
So in our for example, if we had an endothermic reaction, we decrease the heat, would the heat then flow to would the reaction shift to the left?
That's correct. Yep. All right, so we're going to do this example right here. So I'm telling you right here, our reaction is at equilibrium. Okay? How will the equilibrium shift if my volume is increased? Someone raise their hand. Okay? Exactly. So if our volume is increased, our pressure is decreased, and it's going to shift to the side with more moles. Okay? Everyone good on that? What would happen if I add 4 moles of helium gas? What do you guys think? 4 moles of helium gas in that equation. Nothing, right? So helium is not seen anywhere in our constant expression. So if we add gas to it, it's not going to do anything to our equilibrium constant. Like she said, temperature is the only thing that's going to affect our K value. Yes.
Going back to the volume, can you also kind of think of it as like, since if the volume is decreased, there's more space to take up, so the equation automatically goes to more moles to fill it all up.
Yeah, you can think about it like that. Uh-huh.
If you add a different gas, you want to increase pressure, change the
No, so this comes back to the point that K is only affected by temperature. So our equilibrium constant, temperature is the only thing that's going to change it. So yeah, it will increase the pressure of the system, but it's not going to affect whether this drives left or right. Because in this equation we have reactants and products, and helium isn't seen anywhere in those. So the thing to know is if you add something that's not anywhere seen in the equation, it's not going to do anything. Any other questions on that one? Yeah.
So, I'm not sure I can explain this, but imagine if you had like 200 moles of helium. Wouldn't that increase the pressure in like a real world application?
Yeah, it would increase the pressure. But
so, not the fact that there's more helium present, but like the fact that there's like an increased pressure, like could that have an effect on equilibrium?
no. Yeah, yeah.
Yeah, I want to talk about this just a little bit too, because this is a confusing subject because we're talking about pressure and volume. And if I change my volume of my system, it does affect the pressure. But when I say pressure, I also mean something like concentration. So we all remember from Chem 105, we talked about gases. Gases don't react with one another, right? So I can pump in as many moles or as much ATM of helium that I want that won't affect the way that these are reacting with one another. My system, like the container it's in, might feel a lot of pressure, but when we say pressure, we're really sometimes talking about like the amount of moles of the gas we put in, like the ATM, like concentration. Think about it like that. And volume, when we affect the volume, that changes pressure, but that will change it in the way that these react, but they react independently of something that's not part of that equation. So it is a confusing, like there are a lot of things you might think you want to mix in your mind, but try to keep those really separate.
The main thing to think about is if we're talking about pressure, pressure will only affect our equilibrium if we're increasing or decreasing volume. So if we change the volume of the container, that will change the pressure, and then that will cause a shift. But if we're just pumping random gas into the container and making more pressure, it's not going to do anything. Do you have a question?
No,
That was it?
Yeah.
Awesome. Okay, this last one, kind of a little trick. A lit match is placed in the container. What's going to happen? What does fire do? What does it need? Oxygen. Right? So if we're decreasing our oxygen, which way is it going to drive? To the left. Awesome. No. Does anyone have any more questions on this before we switch? Yeah.
Would the heat also affect it? Because the heat is a product in this case.
So I would say the heat,
Potentially.
it potentially could, but the fact that they say a lit match,
That's
it's pretty insignificant. But if I said like I lit a fire, then you would have to take the heat into account. In this case, they're a lit match, they're saying, because that would react with the oxygen inside of that container, would probably not produce enough heat to really mess with my K value.
And for that as well, I'd have to tell you if it was exothermic or endothermic, because from the information you're given, you wouldn't know that. Yeah.
Valid. Okay, so we've gone over Le Chatelier's principle. We understand the things that affect my equilibrium, but don't affect my K value, right? Only temperature affects my K value. So just remember that specific rule. Only temperature affects my K value. In fact, on the right over here, I wrote several equations that will probably be used on this exam. And the bottom one, those K2 over K1, that's dealing with how temperature can affect the K constant of some sort of reaction. So that's one you're going to want to have ready and be able to use. And I crossed out this Kp equals Kc times RT raised to the n. You guys have had to use that equation on your homework assignment. Now, I talked with Dr. Macedoni today, and he said he's not going to have you do that. And the reason I talked to him is because those of you who were in the 9 o'clock hour maybe heard him make an announcement when we passed out that worksheet today. I know that initially, I was helping students with that problem number 2 that had this ice table, and they just gave you, it said K equals something. They didn't say KC or KP. Because our reaction was gases, I thought that would be a KP value. Therefore, we would have to solve for the partial pressures of each one, of each species, in our equilibrium expression to use an ice table. But he meant to write sub C. He meant that to be a KC value. And he announced that, and for those of you in the 10 o'clock, I'm sure he announced that as well. So what I'm getting at is you will not have to convert between the two, and he will make it clear which one you're dealing with, right? So if you're given a KC, you need to make sure you're doing your ice table in molarity, right? Some sort of concentration. If you're using KP, then it's ATM, or partial pressure of those gases, okay? And he'll make that clear, and you'll know which one to use, because I know that kind of got a lot of us this morning, including myself. So he'll make that clear, okay? Let's move on to this problem right here. This is a problem, I can't remember where I got it, but it looks like the problem we did today. We're using the same species. It's a little bit different. Let's read it through. We're given an equation, right? And then we're asked, and it says, given the initial pressures, and then it tells us this information. So initially, we have a certain amount of partial pressure for each species in this reaction, okay? And then we ask, what is the equilibrium pressure of each one? So let's take, 1 minute max, and just get this set up, right? Get this set up of what you would do, and what I want to know when I call back on you guys in about a minute, what is the first thing you should do in solving this problem? I want to know the first thing, okay? We'll go through that. This is a stepwise, systematic way of solving these problems. Definitely need a K. What was it? I have it. That's the first thing. You see that? KP equals 2.15. Bam.
Yeah. 2.15.
All right, that's a minute. So, you can tell me what is the first step you should take to really solve this equation. Ooh, one person, raise your hand, I'll call on you, and then say it loud. Andrew, say it loud.
The rice table?
A rice table. Okay, first step is we realize that this is going to be a rice table problem. Second step, right here.
Find your Q.
Find your Q. Beautiful answer. That is what you need to do. Okay? The reason, who can tell me why that's so important? Let's have you guys answer this. Right here in the middle. Say it loud.
Because it tells you which way the reaction is going to go towards it.
Right, and that is important because, just continue with this, you're on a roll.
Because it'll tell you the signs for the variables. If you can add an X or if you need to subtract.
Exactly. Perfect. So the first thing we do is we need to solve for a Q value under these initial conditions, right? The mistake that is often made, maybe sitting here in these chairs right now before your exam, you're thinking, no, I won't make that. But please don't actually do it on your exam, is to forget that you actually need to figure out what your Q is first, so you know which direction this is going to shift to get to equilibrium, right? A lot of people will just start plugging it in, like most of the problems we see, where the reactants are losing some amount of formed products. In some cases, we're actually going to go in the reverse direction, okay? So, we need to solve for a Q. So what I'm going to do in this case, you guys, because you guys have done a lot of ice tables, I'm just going to write the expressions out, and we're not going to really take the time to go over the math very specifically, but I'm going to write the answers and kind of the steps you need to do, or the intermediate phases of what you're doing here, and then later on you can go back and take this really slow. That's because the algebra, I know that's been a common problem with doing these ice tables. Some of you don't like the algebra. For some of you, it's been a long time for the algebra. That's something that I would advise you to work specifically on, like with your TA, or get us after this review, or whatever you can do. Make sure that you can really do that math. Okay? So the first thing we need to do is find a Q value. So I know that my Q value is equal to my products over reactants. Right? I have to write an equilibrium expression. So I look at this, I say it's my products over reactants. So let's see, my products are these two, so I'm going to have 0.150 times 0.250 over my product, or my reactant here, 0.05. Okay? Now, what is special about this that I use? Why did I not use brackets? Because we're using gases. I know that's a very simple question, but what if he had you choose what was the correct equilibrium expression, and two of them were really close, except one used brackets and one used this? You would see that these are gases. This is how I'm going to write it. I'm not going to use brackets that signify molarity, right? I'm using ATM. So I'm going to solve this through, and I should get 0.75, right? I believe so. Yeah, my Q equals 0.75. So my next step is to determine which way does this reaction shift. And this is the trick we use. We say that K and Q, right, we do 3 comparisons between K and Q. Okay? We say that when K is greater than Q, that means my reaction will go towards the right for the products. What we mean by that? If Q is greater than K, we will actually shift back towards my reactants. If they equal each other, then I'm at equilibrium and don't really have to do anything. So in this case, my Kp is this, 2.15, which is bigger than 0.75. So I'm this top step. So my reaction will shift towards my products. Okay, so it's going to be like we normally see, where the reactants will be losing some amount of X to get to equilibrium. Okay, so let's write this ice table out real quick. I'm not going to do the R part, right? R for reaction. We already have the top. I'm just going to do the ice part. Okay, so let's start with this right here. And we are given, how much do we start with? 0.05. Okay, and then we have this species, and we were given 0.150, and then that par species, 0.250. Again, we're going to be subtracting X here. We decided with our Q's, subtracting X. You guys have seen this a lot. This is going to be at equilibrium, 0.05 minus the amount that reacted to get to my other side.
You're adding X.
You're adding
No, the other way.
yeah, that one's minus. That's
Right
a
here.
plus. That's a plus.
Sorry. This is minus. This is a product, so I'm also adding X. This one, I'm also adding X. And this one is going to be 0.150 plus X. This is going to be 0.250 plus X, okay? So this is my these are what my concentrations will be at equilibrium, if you can see that. And what I'm going to say is my Kp, or 2.15, is going to be equal to my products over reactants. 0.150 plus X times 0.250 plus X divided by my reactant here, which is 0.05 minus X. Okay? Let's see if I wrote down what X is. I did. So when you do this math out, okay, you're going to get, we'll write it really big, we'll put it right down here at the bottom. X equals 0.027. And then if I wanted to just get the concentration of equilibrium, I would plug this X value in for here and solve for what that would be at equilibrium. So I know that for most of you, this is something you've already done a lot if you've been doing your homework. You've done this several times. This is pretty redundant. But there are a few things that I want to talk about in terms of K. Before we do that, question? Can we just say no to it? Well, you mean, can we just exclude it? Well, let's think about that. Our K value is 2.15. What does that mean about my reaction? It's a little bit product favored. It's not ginormously product favored, but it's a little bit. So if I know that my reaction is product favored, that means a lot of my reactant reacts, and I lose a lot of it to form a product. So I can't just exclude my x here because I've got 0.05 ATM that I started with. And chances are, because of what my KP is indicating to me, I will lose a good amount of that to form products in the end. So what I should see when I finish this math out is that my equilibrium pressures for all three of these species in this reaction, those of my products will probably be a lot higher than that of my reactants because of this right here, okay?
In class, we had a problem where we had to assume that it was a negligible difference.
Right.
We need to understand that for the test.
So that's what I want to talk about right now. Let's talk about the power of our K value, like we've done in kinetics. When can I assume, or what were we talking about there? Everything that my K value tells us, and we'll do that for the next few minutes, okay? So first of all, when we did kinetics, we talked about, I know that I stressed a lot that your K value, or that K constant in a rate law, tells you a lot about the order of your reaction, right? Because of those units. Well, for different reasons, your Kc values, or your equilibrium constants, those tell you a lot about the reaction, right? Remember, if those values are very big, right, like 1,000,000, 100,000, or big numbers, then that means that they lie heavily towards the product side. If they are really small numbers, that means that my equilibrium lies way towards my reactants. So at which point can I assume? Well, you can assume, like in this case, we'll try to take this case specifically because we've already got this written up here on the board. I know that my reactant here is losing a pretty significant amount because my K value is a product-oriented K value. It's positive, or it's greater than 0, so I'm going to be more towards the product. If I keep it like this, if I rewrote this like this, 2.15 times 10 to the negative 5. Okay? That is a very small number. What that signifies to me, my reaction is very reactant favored. So of this expression, of this amount of reactant I have here in the denominator, a very small amount, or a very small x value, is going to actually take place. It's going to be small. I'm basically still going to have almost all the reactants I started with. And how I determine that is, he said there's no exact line, but it's usually by a factor of 1,000, right? If you can multiply by 1,000 or divide by 1,000 from your original initial stuff, and you're still far away from your K value, then that means that you could probably assume, like in this case, being to the negative 5 is way smaller by over a factor of 1,000 than 0.05, or close to that, right? So I can assume that it didn't really do a whole lot, okay? So that's what K will tell us in terms of assuming, knowing if it's product or reactant favored. Go ahead.
Is it okay to just never assume and just always solve for the x?
So her question is valid. She says, is it okay to never assume and just always solve for x? Yes. And I would do that almost every time. Unless you're 100% confident that you can assume. It's crazy. This is like to the negative 31 or something. Then you're like, I don't even know why I'm going to do this. You know, just assume and do it out. Now, I know Dr. Macedonian. I'm sure he wouldn't make it that easy. It won't be that difficult either if you've done some practice, but I would do it both ways. It won't hurt you either way.
So what if we have a very large K value, but we also have a large Q value, and they're almost the same?
A very large K and a large Q.
Would that ever happen?
So if you had a super large K value and a super large Q value, still, them by themselves, the K value tells us a lot. If it's super large, I form a lot of products. If my Q value is large, all I'm ever worried about my Q is comparing it to my K. My Q doesn't mean a whole lot to me unless I'm comparing it to something, to my K value. So in this case, I'm going to run through these 3 steps again. I'm just going to say, okay, even if they're all big numbers, I could still have my Q value might be a little bigger than my K, even though they're both big numbers. That's still going to cause a shift, okay? I think that's just about everything I wanted to go over with this. Will you push the board up? With K values being significant and being really important, I think I have another question right here that kind of incorporates understanding a little bit more of what a K can tell us. Let's read this question. I'm given this reaction here, okay? And just, the information is just on the board. I tell you that at 573 degrees Kelvin, my Kc value, or my equilibrium constant, is 4.34 times 10 to the negative 3, okay? And then, I tell you, at 700 degrees Kelvin, this same reaction, the equilibrium constant, is 1.04 times 10 to the negative 4. Is this reaction endothermic or exothermic? We'll give you let's think about it a little bit. I know some of you have the answer. Think you have the answer. We'll talk about it in just a sec. Think about it for 10 more seconds. Okay. Someone raise their hand and tell me your answer and give me an explanation of why, and please turn your volume up so everybody can hear. So, raise your hand, and you also have to tell us why. Connor.
So, I think that it's exothermic because as the temperature is increasing, our K value is decreasing. And so when it's inversely related, we know that it's exothermic.
Valid. Okay, that's a good explanation. And you're right, it is exothermic. And I liked your explanation. It was really good. Does anybody want to explain the same thing he said, because that's right, in a different way? It's not really that different, but even in their way of thinking about it, because what Connor said is 100% right.
If you add heat as a product, and then you increase that or decrease, increasing that heat is going to shift to the left. And that would mean that your K value is decreased.
Yep. So I take the systematic approach, just like you did, and just like Connor did. What I would look at, okay, I have two conditions. One of them's at this temperature with this Kc. One of them is at this different temperature in this Kc. So what I know is that as I increase my temperature, what's happening to the way my reaction shifts? So if I increase my temperature, my Kc gets smaller, and I understand that that means it's more reactant favored now. So if I'm increasing temperature and it's shifting back towards my reactants, that means that heat was a product and I was increasing that. And one thing I've drawn before, for those of you who had me in recitation for Chem 105, was like, imagine a cookie sheet, right? And if I filled this cookie sheet with water and I wrote out this reaction, N2 plus H2 gives me NH3. I'm not balancing it for just reasons. And I figured out it's exothermic, right? So I'm going to have heat as a product. I think about equilibrium sometimes as if I was going to increase my heat, I'm taking this cookie sheet on this side and I'm raising it. Which way will the water run? All the way back this way, right? So I'll cause this wave where it'll rush this way, right? So I know that it will go back with my reactants. Now if I decrease my heat and I took the cookie sheet over here full of water and I tipped it down, which way will the water rush? Towards the right. So that would rush towards my products. Okay? It's just something to help you see that a little bit. Okay?
All right. So next we're going to talk about how your K value changes. Like, you guys are familiar with Hess's law. Remember how Hess's law, you can have elementary steps, and then they would give you like a delta H for the one step, and then you could flip it or multiply it, and then that would change the value of your delta H. We can do the same exact things with our equilibrium constants. So here's a problem that I wrote out for you. I want to give you guys just a minute before I just tell you how to do it. Really think about this, and think about what you need to do to this equation, to these two. So these are our elementary steps, we can say, and this is our final step. Okay? So you need to manipulate these to get this. All right? And then I want you to think about what then in turn you have to do to your Kc values. Or, yeah, Kp values in this case.
Let me move this over here.
Okay.
Or just put the necklace on the floor there.
That's an idea.
Yeah. Okay.